Hi everybody, I'm Sam Stosky, Project Manager for Primus Locus Engineering. With me today is the team of engineers working with me on the County Road 38 project, each assigned to their own discipline as listed. So the County Road 38 project, it will incorporate a redesign of the roadway spanning from County Road 19 to State Road 15, as well as the intersection at County Road 21. There will also be the addition of the visitor center that will have sidewalks spanning from there all the way to the bridge. And then with these designs, there will be stormwater treatment practices to treat for the water quality and flood control volume in the project, as well as clean water supplied to the visitor center from the water treatment plant. So as well as being the project manager, I'm also the water resources engineer. Quick design overview from the final alternative selected from last semester. I have bioswales running on the north and south end of the road, passing through culverts leading to a detention basin. At the visitor center, I have a storm sewer system with grass sections, all leading to an infiltration basin. And on the east side of the bridge, I have a curb and gutter leading to a rain garden with a pre-treatment settling pool. So the first component design was the ditch design. I used Manning's equation to find the minimum requirements for the ditch. Elkhart County standards provided a 3:1 maximum slope ratio. And for Manning's coefficient, it was 0.026 due to a natural straight channel with some grass. Plugging all these in. Oh, and also the West Road peak flow was 3.36 cubic feet per second, which was the minimum requirement calculated last semester. Plugging all these in, I was able to complete this table for the minimum requirements of the ditch. And then plugging in the final ditch dimensions, I found a height of 2 feet, a bottom width of 2 feet, and a top width of 14 feet. This gave a slope of 3:1, which met the maximum slope requirement, and a peak flow for that ditch of 359 cubic feet per second, which is well over the minimum peak flow of 3.36. The next component design was the culvert design. For this, I used HY8, and Elkhart County standards provided a 15-inch minimum diameter for the culverts and 6 inches minimum depth below the road. Again, I used that 3.36 design flow calculated last semester. And the culverts that were designed were the 2 culverts by the visitor center on the north and south end, and the 3rd culvert leading into that detention basin. So for the first culvert on the north end, it took in 5,200 feet of roadway watershed. I used a 1.5-foot diameter concrete culvert, and this spanned under 80 foot of roadway width. Attached here is the profile of this culvert showing the water intake. For the second culvert on the south end by the visitor center, this also took in 5,200 feet of roadway length, and again I used the 1.5-foot diameter concrete culvert. All of this one spanned under 70 foot of roadway width. The third culvert on the east end took in 2,900 feet of roadway watershed, and similar to the other two, I did use the 1.5-foot diameter concrete culvert, and this one also spanned under 80 foot of roadway width. The next component design was the detention basin on the east end. Using USGS, I found the water table depth to be 8.2 feet at this location. Elkhart County standards provided a 3:1 maximum slope ratio, and I used level pool routing with a peak runoff rate of 3.36 cubic feet per second and the time of concentration of 1.56 hours to do this. Using these values, I got the inflow-outflow hydrograph, which highlighted the inflow into the pond as well as the outflow, and the intersection highlighted the peak storage in that pond at that time. So with the final dimensions used in level pool routing, it was an elevation of 8 feet, which is close to the water table but still sufficient, and then the dimensions going up at a slope of 3:1. The orifice size was a 0.5-foot diameter orifice, and through level pool routing I got the peak storage to be about 124,000 cubic feet, while the volume of this pond can now hold 155,000 cubic feet. For my future design, I will design the storm sewer system, grass sections, and infiltration basin by the visitor center, as well as the curb and gutter and the rain garden on the east end of the bridge. I'll now pass the mic to Mike.
Thank you, Sam. I'm Simeon, and I represent the environmental engineering team here at PLE. The primary design objectives for the environmental portion of the County Road 38 reconstruction include providing the visitor center with clean drinking water while supplying it at an average rate of 1 million gallons per day, Some preliminary work that occurred in the phase 1 portion involved a water quality assessment of the Elkhart River, in which contaminants of concern were identified and target levels were set to help guide the design process. So the design includes 5 overall components. The first 3 components will be discussed in today's presentation, and the 4th and 5th component will be incorporated into the final presentation. So the first portion is the water intake, which involves the extraction of water from the Elkhart River to be treated at the treatment plant. One of the constraints is that the extraction rate must be less than 3 to 5% of the Elkhart River flow rate for a permit to be granted. So using the long-term median flow rate provided by USGS and some calculations, it was determined that this extraction rate would be satisfied. An additional constraint was separating the inlet from the future wastewater discharge point, which will occur downstream of the clean water treatment site. So the EPA provides criteria, and using that and some engineering common sense, the inlet was placed 500 feet upstream of the clean water treatment plant location. And finally, some consideration for marine life was taken into account, so a velocity cap and fine screen will be added to the inlet pipe. So the results of this included dimension calculations for the pipe and sizing the pump to be able to supply the flow rate for the water treatment plant. The second portion of design includes the coagulation and flocculation basins. Coagulation involves higher speed mixing with the addition of coagulant blends, while flocculation involves slower speed mixing that promotes higher rates of settling. One of the constraints with designing the coagulation was determining the alum dosage, as it's something that requires on-site testing, often known as jar testing, to best determine, since there's a correlation between reducing the turbidity without making the water too acidic. So while other studies were used to help prepare calculation, on-site testing will be needed to determine the optimal alum dosage. And the results indicated the tank dimensions for both the flocculation and rapid mix basin, while also providing impeller lengths and motor requirements to spin those impellers. So the water will flow in through one of the 2 compartments and go into the smaller basin, which is the flash mixing, and then going into the 3 larger basins, which are the flocculation basins. And then that will lead into the sedimentation portion of the water treatment, in which splitter box will once again be used to separate the flow into 2 different locations, because 2 clarifiers will be used. Circular clarifiers were selected in phase 1 due to their geometry that allows for longer detention times and higher rates of settling. And in general, just like two flow lines exist for the flocculation and coagulation basins, 2 separate circular clarifiers exist to design for redundancy, because maintenance will be required at some point in the future. So each one of these will be able to handle the daily maximum flow rate when the other line is taken off. So the results once again indicate the tank dimensions, and as well as the sludge loading rate. The water will flow in underneath and come up through the middle and then settle to the outside. And the sludge scraper on the bottom will rotate around to collect sludge and remove it so it can be taken off-site. And the final element today is a preliminary, or 10% contingency construction cost calculation. The EPA's water treatment cost estimator was used for this, so this consumer price index was used to determine an inflation rate, and RS means was used to determine a city cost index of South Bend relative to the rest of the United States to help estimate the construction cost. So with that, the construction cost was determined to be just shy of $9 million for the environmental portion. Future design will include the rapid sand filtration along with the disinfection before finally entering the water distribution network. I will also prepare an operation and maintenance cost calculation for the next presentation. Thank you. Here's Theo.
Hi, my name is Mateo. I'm here representing the structural department of PLE. So to date, for the visitor center at the County Road 38 reconstruction project, first and foremost, we decided the structural building dimensions, and from that we were able to determine what we wanted our layout to be in the building. From that layout, we got our occupational loading using the ASCE 716 standards, and from that we have thus far done the gravity loading design in Floor for the mezzanine level. This is, again, the general construction that we have. It is a first floor which will have, again, a museum, a gift shop, a space for maintenance workers to be in, as well as like the general lobby and entryway, with the restaurant on the second floor, heading out to just kind of a terrace area with a roof garden and also open outdoor spaces. Here are the general criteria, constraints, and assumptions. So first and foremost, provide an area for drivers to rest or local residents to rest where they can have entertainment and shelter from the elements. The design needs to be a minimum of 40,000 square feet with 12,000 square foot cover space distributed over 2 stories. For the occupational loading, I used ASCE 716, and IBC is going to be used for any other standards that are not covered by ASCE 716 or not found in any of the LCART standards. And the following are all standards that were used in Floor to help design all of the members. And I used the Volcraft Steel Joist Manual for the joist girder members that would not be designed by Floor. So here's the general member layout for that mezzanine. In total, it's 41,800 square feet. And we also have the additional covered space, which is 3,450 square feet. The first floor itself is 32,800 square feet, and the second floor, the restaurant, will be 9,000 square feet. So this is kind of the roof level for the first floor. We have 40-foot spacing here, 50-foot spacing going across with 25-foot spacing as well for those smaller sections. Most of the building will be supported by gravity loading via the long span joist, which will be supported by joist girders. And in those areas where we are concerned with lateral loading, we also have W sections in place for those moments, and we will be further analyzing that with 3D. Here's kind of the distribution of loading. This is our deck that we have going across the entire building. And then on the right here in green is the loading for the terrace, which is 100 PSF. For the roof garden, which is in red, also 100 PSF, and the restaurant conveniently in blue and 100 PSF. Here are the loadings that we have. So again, restaurant, terrace, and roof garden all are 100 PSF live loads. Then for the snow load, using the ASCE hazards tool, we were able to get 44 PSF snow load. For roof, we have 10 plus 20 dead and live load. And for the composite decking used, we have a dead load of 44 PSF as well. This is kind of a more intricate look at some of the design members in one of the more difficult areas. As you can see here, the long span joist over 40 foot being supported by these joist girders. And then we have in these 25-foot bays, smaller long span joists again. And then where the loading gets a little bit more tricky, we place these W sections where it's a lot smaller spans and where there could be additional loads more than just the gravity loads that the joist can take on. Here's a rundown of the general members that we have thus far. As you can see, mostly long span joists supported by those joist girders. And then we have those supporting W-shaped beams where we take on the loads that the joist girders or the joists may not be able to. For future work, we need to analyze the second floor, which is that restaurant in Floor. There are some setbacks because Floor doesn't necessarily like to do trusses, so I'm going to go through Reza 3D and do that. And after that, we'll be able to run the lateral loading analysis in 3D for the entire building. And after that, I'll be able to have a rundown of all of the materials that I need and run a cost estimate for the final design. And with that, I'll pass it over to Vince.
So I'm Vance with the Transportation Department. So this is the overview of our transportation design. So So the main objective of this design is to design an intersection for pedestrians, bikers, and motorists to have a safe form of crossing pretty much. We also plan to add a center turn lane to the east of the intersection of County Road 38. We also plan to add parking that meets ADA standards for people with disability who need quick accessibility. And we also plan to add a multi-use path on the south end of the roadway for pedestrians to connect with the visitor center. And I also designed for a proper intersection turn radius because we have truck traffic on this road, so trucks need a wide enough space to turn. And we need to have a proper number of lanes for the traffic flow going through this roadway. So these are some of the criteria, constraints, and assumptions. I took most of them from the NDOT design manual. So the lane width that we're using is 12 feet for the roadway, just standard. The paved shoulder width is about 10 feet, and also there will be 1 foot of additional aggregate for the shoulder. We also have a 10-foot center turn lane and a 14-foot ditch on each side of the road. So this is the typical section for the roadway. As you can see, we have our shoulder, our mainline pavement, our ditch with our 4-to-1 side slopes, and also the concrete biking pedestrian path with the center turn lane. So these are some of the details for the intersection. As I said earlier, we're going to have a larger turn radius for larger vehicles, specifically the WB67 truck. So 125 foot should be adequate for that. We're also going to have dedicated left turn lanes going westbound and eastbound to alleviate the higher traffic flow. And we're also going to have islands to separate turn movements from like through movements pretty much. And this is just a visual. As you can see, we have the turn lanes for the left and right and also the channelized islands. And this is the parking for the visitor center. So we're going to have 133 parking spaces in total. It was determined that we would need about 130, but we decided to go with a few extra. Each space will be about 11 feet wide and 20 feet long. There's going to be 2 handicap van accessible spots for the larger vans with the ramp to be able to come out and allow the person to get out in an efficient manner. And we're also going to have just 6 regular handicap parking spaces for people who just need to have a handicap space close to the building and get quick and easy access. So for the future work, I plan to have our detour plans. I still need to figure out which roadway is the best for the traffic to basically go on in an efficient manner. Also need to figure out additional pavement details, whether it be permeable, non-permeable, and that needs to be coordinated with the water resources engineer for the parking lot and the roadway. I also plan to complete my multi-use path details for the south end of the intersection. And I also need to do a detailed cost analysis of how much this will cost. Thank you, and are there any other questions?
Sam? Start with simple or hard questions, Sam?
Give me the hardest one you got.
The hardest, okay, go back to the number. So what controls your design? Is it the headwire or the tailwire in this case?
Think of the headwater.
You think?
Yes.
Did you include that in your assumptions of?
Well, in HY8, there's this whole table of data you input, and I didn't put all of those values. I just took out the ones that I thought would be most relevant for this presentation. So I could bring that to your office and show you what I put. Can't really.
What did the program HY8 state for you? Does it say it is a headwire or like a tailwire control?
I'm not really sure. That is a hard question for me. I can't answer that right now.
Well, let's ask you the simple question.
Okay.
And when you use the term maximum slope of a 3 to 1,
Yes.
is it maximum or minimum slope?
So that-
is 2 to 1 is there or a 3 to 1 is there?
3 to 1 is the highest you can go. You can't so the slope is it's like you're rising 1 foot and going over 3 foot.
So this is the minimum, not the maximum. So it can be 4 to 1.
Yes.
Yes.
Yes. I guess I did phrase that wrong. But that's just how the Elkhart handbook phrased it. Elkhart.
I'd go with maximum.
It's the maximum steepness.
That's
Yeah.
as steep as you can
Yes,
go.
yes. So I got a question about that slide.
This one right here?
Yeah.
All right.
So Manning's equation, there's a typo. I hope it's a typo and that you didn't use it in that form in your design. Maybe somebody on your team who's in water resources in class can,
What I got?
The one,
Slope should be to the. Oh, no, I did it to the 1/2,
Okay.
but I know that. We can check that.
okay.
I can verify I did it for him, no.
I did do 1/2, I got this equation memorized.
Technically, that's a friction slope, but, right?
Yeah,
So-
no, I did it to the 1/2,
Okay. Okay.
I guess we could.
can I continue with my question?
No, you're done.
Someone wants
Okay.
to.
Matthew, I have a question, a simple one for you. I think I just, a clarification, not Sim, in there. You mentioned that you want to be handling, I know you said you did not do the lateral loading yet,
Yeah.
but you, one statement alerted me is saying that you're going to be using W sections for that once you transfer it from the
Yeah.
floor to 3D, RISA 3D. Now, how do, in general, and I don't want to talk about your design,
Yeah.
but how do you resist lateral loading? So what methods or mechanisms you use?
I was, can I talk about my design real quick? Because I can take over and put
Go
my
ahead.
answer.
I just want to know how you want to
Yeah.
resist
The
lateral
W,
loading.
we put the W sections in just to kind of prepare for the lateral loading and to have some assistance, but that's not gonna be the main system for that lateral bracing. We have the masonry wall around, which should kind of help with some of the lateral loading, but in my mind, it would be a lot of expiration we might need to use for that lateral system.
Good answer.
But that-
Thank you.
those
That's
W
what I'm
sections
looking
just,
for.
prep, just for extra, yeah.
I'm not. So,
I want to ask about, back to ditch slopes. Yes. But in the other direction, longitudinally along the road,
So-
what is the slope of that ditch?
Like, are you talking about in this graphic?
Yeah, one of those.
This one?
No,
My graphic, or?
right. Longitudinally along the road,
Yeah,
where is the water flowing? And how do you control that?
Parallel to the road.
Parallel to the road.
In the ditch.
so like, the water going this way?
no, going,
Going this way or this way?
The water's going that way towards the
Be-
detention basin.
be- And have you designed that to happen?
Oh,
Is
the
that-
slope of the ditch going that way, is that what you're asking?
Right, right. Because you can't say it's a 14-foot ditch
Right,
if later on it gets deeper because you have to go down further, so
Yeah.
it could be a 20-foot wide ditch, you know, and that.
I don't know the slope.
Have we looked into that yet?
Yeah, it's a good
Jen?
question. I don't know the slope necessarily for this ditch going here, but I did follow the contour lines. And
Okay, well, you know,
It-
they may go like that,
Yeah.
and you can't get the
I guess
water
I
uphill.
should
to
double
the-
check into
we need
the
to-
slope of that ditch entirely and
just-
see if maybe it gets deeper or wider.
And just to see that all the
What-
water is going the same direction,
Yeah.
maybe it's not.
what did you use in Manning's equation? That's what he's asking.
Yeah,
That
yeah,
slope
yeah.
is used in Manning's
Basically,
equation.
Into that wrong equation, what did you?
Oh,
See, now I get it. Yes, I use the slope of the length of the bioswale and the change in elevation.
That's it.
And that,
Is that relatively constant slope though? or-
I'm pretty sure it was. I guess I should double check before I give you a
Yes.
answer yes. I should probably just say yes if we don't ask any more questions. I think it is constant. I'm gonna double check that. That would be a big change if it's not. But it's a good point. Thank you.
Any other questions?